No.
Matt, take your quiz so I can figure out what I did.
Don't tell me what to do, Traves.
Alright, the quiz scores from Friday have been posted, so you can, in your spare time, check out and see how you did. I still have a few people that need to take it, so just like the test that we went over, as soon as they do, we'll get them back and go over anything that you want to. Okay, but the scores are in so you can see how you did. In the meantime, we're going to move on to our next section on page 61, and we're going to be looking at domain and range a little further. Okay, I've kind of been telling you throughout the year so far that we're going to eventually get to this. Okay, so here it is. I'm thinking this isn't going to be too bad because we've already spent some time talking about domain and range, at least when we're looking at a graph, trying to figure out the x values versus the y values. So I'm thinking, I'm very optimistic, okay, at least for today. We're going to get into some more analytical things, we'll say, with domain and range. Maybe we're going to take the graph away and just take a look at an equation and try to figure out domain and range. But that's kind of some high-end stuff that we're going to do tomorrow and later this week. Okay, but for right now, we're just going to practice domain and range. We've already explained or defined domain and range this year. We said domain represented x values and range represented y values. But we're going to make that a little bit more specific. Okay, that's a very generic definition, some way to help you remember the difference. Okay, but it's a little bit deeper than that. So domain are x values, that's true, okay, but they're x values that result in a y value or give a y value. So if you plug in an x, you would get out a y. So x values that give y values. Basically, if you know an x and a y, you have a point on your graph. That's what we're trying to determine. Where do we have points on the graph? Range is very similar. So we have y values that have x values. Okay, y values don't give x values because y values are the dependent variable. Okay, so more formal definition for those. What we're going to try to do is take a look at 1 through 6. Some of them are not too bad, other ones get a little more complicated, but we're going to practice dragging our pencil and identifying where do we have our graph. Okay, left to right, low to high, figuring out domain and range. So if we start on number 1, we'll go left to right first. Where does it seem that our graph starts? Which x value? -4, can we touch it? No, because open circle. All right, so we'll start with -4 with a parenthesis. As you drag your pencil across, you have all these closed circles on the graph. I know they're not big and bolded, okay, but those are closed circles, those are points. As you drag your pencil across, when do you stop having a point on your graph? Will we ever stop? No, because we have that arrow. Okay, so we can go forever to infinity, and we'll close it off with a parenthesis. Now, just like how I was talking about previous mistakes that student makes, I have seen people say that we would go from -4 to -infinity because that arrow is going down. Okay, and I completely understand why some of you might write that, but we got to remember the direction in which we're moving our pencil. Okay, if we're going from left to right, the further you go to the right, that means you're getting more positive. So not only is this arrow going down, but it's also going to the right at the same time. Okay, so be careful again with those arrows. Let's try low to high for range. So if this arrow is going to go down forever, lowest we'd have is -infinity. And as we drag our pencil up, notice all of those points on our graph that we have. We got to eventually ask ourselves, when do we come to a y value that does not have an x value? Okay, where do we have to stop our range? It's going to be 5, and can we include that point? No, because it's another open circle. Okay, so we're going to practice dragging our pencil left to right, low to high, asking ourselves where can we touch a point, where can we not, can we include it, can we not, bracket, parenthesis, all those different characteristics. Do you guys feel kind of comfortable with domain and range up to this point to try the next 5 on your own? Or do we want to go through them together? You want to try them? Go ahead, okay? Try 2, 3, 4, 5, and 6. Some are a little bit easier than others, some are a little bit more complicated than others, but at least give them a try. See kind of where your base knowledge is.
Yeah, I know, that's what I thought. So I'm thinking that we start. Well, the asymptote is it's an open circle too, because you can never reach that point.
That's what asymptote is.
Yes.
Congratulations.
So an open circle. That's it. That's enough one. That's an circle. That doesn't make sense. So 3 and then circle. And then U and then 3.
There's an asymptote. Simpson.
Oh no, there's an open circle. Oh wait, no, that's on the bottom. Does that mean that's the more space? And that's a lot of space. Space arrows. We got it. That's a 4.
Look, I was wrong when I fixed myself. You didn't catch it.
No, the most important of all that is every single thing there's close.
Really good.
Today,
Alright, so no, yeah.
No, that's
I want to go.
Alright, negative infinity, and then positive infinity.
Mine are really bad. Okay.
Because last time I was all pissed.
Assuming a 3,
I wanted to unenjoy my life.
f of x equals c.
oh yeah.
There's so much infinity.
I know.
What is the domain of these numbers?
Wait a minute, why is there's an assembly piece. Gotta love them assembly pieces. Wait, is that an arrow? Question. Is that an arrow? Okay. Those are also
It goes up.
Robbie, do you know how to do it? Wait, is the asymptote thing just normal?
Absolute value. So that's this boy.
You're a point that's not.
Well, and that is the same for range. Yeah, but we don't care about range.
I have a
This one.
And then here's quadratic.
Ours continuously goes this way.
Yes. And that's the same.
I had a question. I don't know
You like my quadratic?
I'm dragging
That's exactly like mine.
the whole.
Just to give you letters, you have to consistently make mistakes just so you're not trying.
Eight left.
Wait, Robbie.
So it's like a half, so like I cut it off here. Gotcha. That's what I thought. Oh, I forgot about X. Oh, Robbie's a closed circle, dude. Look at him.
Oh, I hate There is no solution.
You guys would just be like confident in like your 5th period class, and then all of a sudden I'll like kick down the door.
Oh,
I Spanish anyway.
that is not the main reason. Identify the domain range or just the remember the domain of each function.
Do we do that here? Yeah, think about it.
Oh, wait. We can just
First
do
off, I
it.
get it.
We can just do it.
Wait, so Robbie, what do you have for the domain for 6?
What
Negative 3,
Wait.
1, yeah. 2 is 4, and 4 is okay, I wasn't
Negative
stupid.
one. Here, let's try and do these values
say that before,
because
they'll be like,
because we're gonna have to. So might as well punch this. So think about it. Negative 2 squared. I need this kind of see that.
Smart.
Smile.
Smart.
Smile. Smile. Go. Smile. Smile.
All right, let's check them out. Some of you are still working, which is okay. All right, so you can keep going. I think these kind of got a little more trickier as you went, right? All right, let's see how we did. So number 2, if we drag our pencil left to right, notice how we have an arrow on the left-hand side. So that's going to go forever to the left. So negative infinity. As we start to drag our pencil across, we got to ask ourselves, when do we come to a point that does not have a closed circle? Somewhere. Okay, something interesting is going on at 1, right? Because we have that open circle. So if you look at that x value of 1, notice how there's no closed circle at that same location to kind of counteract that open circle. So this location of 1 is an x value that does not give a y value. Okay, it does not fit our definition of domain. So we'll have to stop at 1 because we only have closed circles from negative infinity to 1. Now we do have more graph to trace, so we'll throw in a u and we'll pick up at 1 again. As we drag our pencil to the right, we'll eventually get an arrow, so it's going to go forever to the right. How'd you do? Pretty good? All right, let's try range. So low to high, we have that arrow on the end, so we'll go down forever. As we drag our pencil up, we eventually encounter that same open circle again. So we got to ask ourselves, is there a closed circle somewhere at that same location, in this case our height, to counteract that open circle? The answer is yes. We happen to have one right there. Okay, so even though there is an open circle somewhere, we do have a closed one. So this is a y value that has an x value, specifically at 3. So we can continue to drag our pencil. We do not have to skip over that spot. If we continue to drag, we'll eventually encounter another arrow. So that's going to go up forever. So positive infinity. How do we do on number 2? Good? Okay, let's check out 3. Left or right, arrow on the left-hand side, so negative infinity. As we drag our pencil across, something interesting is happening at 1. Notice how we do have a closed circle at some point. Even though there's 2 open ones, we still have a point existing. So we can continue to drag. We'll eventually encounter another arrow forever to the right, so positive infinity. All right, if we do range, low to high, lowest looks like negative 3 with an open circle. As we continue to drag, keeping the arrows in mind, we'll eventually reach 2 that has an open circle, but notice how there would be a closed circle somewhere else at that same height. So we can continue to drag, and we'll eventually reach another arrow for positive infinity. How do we do? Good. We want to go over any part of that one? All right, let's check out 4. Left to right, we have an arrow, so negative infinity. As we drag, we get to negative 1 that has some open circles, but no closed circle to actually count. So we have to skip over negative 1. If we continue to drag, we'll go from negative 1 and looks like we have to stop at 5. And that would be a parenthesis for the open circle. All right, so for range low to high, we have to be careful. It looks like it would start at -3 because that's where the V shape is, but that arrow on the end would go down forever. So we'll go from -infinity. As we drag our pencil up, we do have an open circle, but there is a closed circle somewhere else at that spot, so no biggie there. As we continue to drag, there's another open circle, but there's a closed circle somewhere else, so no biggie there. As we continue to drag, notice how we get an open circle with no closed circle, so we'll stop at roughly 3.5. How'd you do? We're on a roll. All right. Next one, left to right, -5, open circle. As we drag, we get to -1. Even though there's an open circle there, there's another closed circle, so that point still counts. We can continue to drag. We'll get the arrow, so positive infinity. Low to high, start at -3, and we can count it. That's our vertex. As we continue to drag, we get an open circle, but there's a closed circle somewhere else. As we continue to drag, we get another open circle, but there's still a closed circle somewhere else. As we continue to drag, we eventually get the closed circle at 4, but there was an arrow on the end of the parabola which would go up forever. So positive infinity. Did we catch those tricky spots? You got to be careful with the arrows. All right. We ready for the mother of all of them? The last one? Left to right. I know it's kind of hard to see, but there is an arrow right there. So it would start at -infinity. As we drag across, we get to -1. There is an open circle, but there's a closed circle there as well, so we can still count that point. If we continue to drag, something's going on at 2. Do you know what that's called? That vertical dotted line? It's a vertical asymptote, okay? And at a vertical asymptote, you do not have a graph. That's why if you look at the left-hand side, the left and the right in this case drastically go down. Okay, they're not connected because there's no graph there. So if we do not have a closed circle at that asymptote location, we have to stop there. So we're going to skip over 2. As we continue to drag, we eventually get an open circle at 4, and there's no closed circle there to counteract it. So we'll skip over 4 as well. And if we continue to trace or drag after 4, we'll get another arrow going towards infinity. So that domain was rather long. You had to skip over 2 spots. Okay, 2 and 4. For the range, we had arrows on either side of that asymptote going down. So we can go down forever. As we drag up, we eventually get an open circle, but there are closed circles in other spots, so we're all good. As we get to another open circle, there's a closed circle somewhere else at that height, so we're all good. And we'll eventually get the arrow on the end for positive infinity. How do we do? We do okay? All right. If we made a mistake, do we know why? We're okay with that? Perfect. Okay. Now, I would say these domains and ranges are very involved. Notice how we just skip over some numbers, especially for this last one. I'm not saying every single graph is going to look like this or be like this. But if we can do these more complicated ones, the other ones we do this year should be no issue. Okay, so we're going to practice the difficult so the easy are even better. What we're going to take a look, though, at are some basic equations. Remember, like Travis and River. We've talked about basic equations so far this year, like in terms of the parent functions. We're going to see what those domains are. Okay, range is a good characteristic to know, but domain is a little bit more important, I would say, because we're usually concerned with what numbers we are able to plug into an equation okay? And those will result in the numbers we can get out. So we want to know what we can plug in, okay, whether it would work or not. These four at the bottom we are already very familiar with, so we're going to take a look at what those graphs look like and then determine their domains. So what does the graph of a constant function look like? If you were to graph like y equals 5 or y equals 2, what would that graph look like? Can you draw it or describe it? Yep, straight line, okay, so something like that. So if you were to drag your pencil from left to right on that straight line, what would the domain be? How far left could it go? How far right could it go? Do we have to skip over any values? I see arrows on both ends, and there's no hole or asymptote in the middle. So looks like we can go forever to the left and forever to the right. Okay, negative infinity to positive infinity. We can refer to that as all real numbers. This is basically telling you you can substitute in any number you want and you'll get an answer out. Okay, all real numbers. Do you know what the symbol is in math that represents that phrase, all real numbers? Like instead of having to write on your paper, all real numbers, there's a little symbol. Yeah. It's an R with a what? Kind of. It's a double stemmed R. So you have two lines and then the rest of the capital R. So this is just a symbol that means all real numbers. Okay, every single number could be plugged into that equation, and you'd get a point out. Another function we should be familiar with are lines. So depending if the slope is positive or negative, your line could go up or down. If you were to drag your pencil left to right on a line, what would the domain be? Forever to the left, forever to the right, no holes, no asymptotes to worry about. So all real numbers. Another shape for absolute value are the V's. Now depending on any transformations, the V might go up, but it also might go down. Okay, if you were to trace your graph left to right, just for the domain, notice how we can go forever to the left, forever to the right, because we have those arrows and there's no holes or asymptotes to skip over. So we have another all real numbers. Quadratics are the U shape. So again, depending on transformations, the U might go up or it could go down. If we were to trace it left to right, we would never have to pick up our pencil. No holes, no asymptotes. So all real numbers. So notice how more realistically these basic graphs that we're familiar with, they have much simpler domains, okay, than the complicated ones we had at the top. Do we see how not everyone's going to be too bad? Okay. We are going to talk about some other equations though. So all of these are all real numbers forever and always, but there are two, sometimes three special cases that we're going to have to be kind of careful with. So if you look on the next page, we're going to take a look at three different graphs. One of them is a fraction equation, and then a square root and a cubic. A fraction equation by name is referred to as a rational function. Maybe that sounds familiar or not. Okay, but if you think about ratio is normally comparing two things, aka a fraction. So just for practice, I don't think it'd be too bad. Let's go ahead and try to drag our pencil left or right on these graphs just to see what the domain might be. Right, so on our rational one, if we start on the left-hand side, we have an arrow. So we can go to negative infinity. As we drag our pencil across, we encounter that vertical asymptote. Okay, there's no graph there. So we'll have to skip over -2. If we skip over -2, that's where the next interval will start. As we continue to drag, we'll have to skip over +2 because there's an open circle there with no closed circle somewhere else. And our last interval will go from 2 to infinity because we have an arrow on the end. Okay, so that graph was a little bit more complicated. We had to skip over 2 spots, that vertical asymptote in that whole location. So this one was not all real numbers. Okay, we just had to skip over 2 places. The square root one is also an example of a graph that does not have a domain of all real numbers, because if you were to trace this one left to right, notice how left would be negative infinity because of that arrow. And then as we drag our pencil to the right, the square root graph looks like it stops at 5. And that's where our beginning point was located. So if there's an actual point there, we can use a bracket. The cubed root one, though, if you take a look at it, we have arrow on the left, arrow on the right, and there's no open circle or asymptote in the middle. So this one looks like it's going to be all real numbers, at least in this example, but we'll eventually get to some that are a little different. Okay, so not every function is going to have all real numbers. Sometimes you might have a beginning or ending point, like the square root does. Sometimes you have those holes or asymptotes, like the rational one does. We have to be careful if we have to stop or skip over any place. So I know that we can find domain based off of a graph. You guys clearly did that before. But we're eventually going to be taking the graphs away and just looking at the equation itself. Like, how can we determine what numbers would work just by looking at what it looks, or what the equation looks like? Okay, so this is going to kind of lead us into that. Pretend for a second that we did not have this rational picture. Okay, we already know what the domain is. We're going to try to figure out what it might be. Okay, what are some numbers that do or don't work? So you could sit there forever and just pick random numbers to see if it would work, if it would not. We're going to see what that would kind of lead to. Take a look at this first one. We're going to test the x location of -2. We're going to see if we get out a point or not. So if you were to plug in -2 into all of your x's, looks like we'd get 4 minus 2 is 2, minus 6 is -4. And if we were to plug in -2 in the bottom, we get 0. What is -4 over 0? Undefined. Good. Okay, some people want to say it's 0. Again, I completely understand why. But where the 0 is located is pretty important. Okay, if you have a 0 in the bottom of a fraction, that's undefined. Whereas a 0 in the top of a fraction is 0. Okay, so we got to kind of remember the difference between the two. We got to be careful with that. I'll never forget my elementary or middle school teacher, whatever grade you are, when you start to learn about fractions and zeros, she always said that if you think about zero as an egg, like if you were to go shopping, you do not want to put your eggs in the bottom of a shopping cart and then all of your other stuff on top of them, because you'd crack your eggs, right? So a 0 in the bottom is undefined, because unfortunately the eggs would break. You do, however, want to put your eggs on top of the shopping cart. That way they stay an egg. Okay, nothing cracks. So if that analogy helps, okay, if it helps one of you, I did my job for the day. All right? But that's always what I think of. It always brings me back to when I was little. Okay? Let's try -1. So if you plug in a -1 up top, 1 minus 1 is 0, and we're left with -6. 1 minus 4 is -3. Looks like we're left with 2. So how can we tell, based off of these numerical results, whether -2 is a part of the domain, whether -1 is a part of the domain? Remember, domain are x values that give y values. What can we say? What conclusions can we make? What do you think, Hadley? Because? There. It's what? It's an x value that gives a y. Okay, so x equals -1 is a part of the domain, but x equals -2 is not. Okay, So without the graph, we can start testing values, whether they are, whether they aren't. And notice how this kind of makes sense, because when we wrote the domain up top, notice how we had to skip over -2 because there's technically no point there. That's what this is telling us. Notice how the y value was undefined. Okay, there's no point. But notice how -1 falls within this interval between -2 and +2. So this is telling us any number in between -2 and +2 would work. Okay, you would get an answer out. And that answer in this case was +2. So we can start testing values. Now, I don't know about you, but I don't really feel like testing every single value between -infinity and +infinity to see if it would work or not. Okay, so this is just kind of a way to get an idea about what the domain is, but there's no physical way we'd be able to plug and chug every single number. So this is when we're going to have to get a little strategic on how we start to analyze our functions. Okay, what are we specifically looking for in an equation to determine if it works or not? Okay, if an x value works or not. So Belle's gonna ring a little bit. We're gonna stop there for today. We're gonna try some other points for the other functions, but eventually we're gonna just look at the equation and know what the domain is. Okay, we're gonna talk about some shortcuts.
Pattern is different. Pattern is different.